In this lecture, I am going to introduce you to the modal analysis and how modal analysis can be performed inside Ansys Workbench. So, in order to access modal analysis, you need to go to the analysis systems. In the analysis systems, you need to select the modal analysis system and drag it and drop it on the project schematic. As I have told earlier, the options, the steps you need to perform will be from the top towards the bottom. So basics of free vibration analysis. So in modal analysis, we are going to conduct free vibration analysis, and the one is the pre-stressed vibration analysis. So the first we are going to learn about basics of free vibration analysis. So what happens here, see, for a linear equation of motion where mu double dot plus ku equal to 0, here usually there will be a force term, but what happens in free vibration analysis, we are not going to apply any types of loads on the body. We are going to constrain the body, and then we are going to find out its natural frequencies and mode shapes. That is why this f term is 0 here, and then this k term is nothing but the stiffness matrix, and this is the mass matrix. So this is nothing but the displacement, and this is the acceleration. So if you take this displacement in its normal form, the harmonic motion equation is psi I sine of omega I t plus theta I, but when we differentiate it for 2 times to get the acceleration, we are going to get this particular value. So we are going to substitute this particular value in this particular equation to change the equation into this form, where k minus omega square into m into psi I equal to 0, because remember this is 0 because this is a free vibration analysis. So as shown in the previous slide, the final equation is k minus omega I square m into psi I equal to 0, where k and m are constant because we are going to perform linear modal analysis, where we assume linear elastic material behavior is present, small deflection theory used, and there are no non-linearities that have been included. Here there should be another term matrix known as the C, which is not present. C is nothing but the damping matrix. What is happening is, in the free vibration analysis, we are not going to consider the damping effect also, and as I've told you, we should be having a force matrix which is also not present, because in the free vibration analysis there is no excitation of the structure, or there is no external excitation of the structure. And C, the structure can be constrained and the structure can be unconstrained. So coming to the geometries, we can use both solid bodies, surface bodies as well as line bodies in order to perform the modal analysis. In some cases, we can use the feature of point mass or distributed mass to add mass without having any additional flexibility that is being added to the modal analysis. Then coming to the material properties, for any for any type of dynamic analysis, the major options or the major material properties you need to define are the Young's modulus, Poisson's ratio and the density, because from the Young's modulus and Poisson's ratio it is able to conduct, or it is able to create the stiffness matrix. But if you want to create the M matrix, which is the mass matrix, then you need to specify the density of that particular material. And coming to loads, there are no structural as well as thermal loads are applied or can be applied in the free vibration analysis. So any type of structural or thermal loads we cannot apply directly in modal analysis. And then if the supports of the body are not given, then the body moves in a rigid body fashion. So what happens if the body is in a rigid body mode, the frequencies, the first 6 natural frequencies of the body will be 0 or nearly equal to 0. And remember, the choice of the boundary conditions will affect the mode shapes. Depending on how we constrain the geometry, the mode shapes of this particular, the frequencies and the mode shapes of that particular object is going to change. Then we can use different types of contacts here in modal analysis also. Then in the solution settings, we can find out, we can set the software to find out the number of modes we want. Like for example, if I say I want to find a 12 modes, I can just give an option here in the analysis setting, or otherwise if I want to find out the frequency between some range, like for example here you see I want to find out the frequencies of the object between 100 Hz to 500 Hz range, so I can also give it like this. In addition to all of these things, I can also ask the software to calculate the stresses and strains and reactions that are occurring due to this particular type of vibration, this particular vibration at the natural frequencies. Then coming to the results, based upon no excitation or there is no other external force that is being applied, we are going to get the mode shapes as well as the natural frequencies. Then coming to the next type of modal analysis, which is the pre-stressed modal analysis or vibration analysis. So what happens in the previous case, we haven't had any type of forces that are applied, but what happens, see, if in the case of guitar string we want to analyze the natural frequency of this particular string, so what happens, this string is attached to this guitar at some tension, with some tension. So in order to simulate such type of cases, we need to be performing this pre-stressed vibration analysis. Here also, for example, this particular say what is the cables that are used for attaching this deck to this pillars, they are also under some pre-stress. So what happens, while in if the pre-stress that is applied is in tension, it will cause the frequencies to increase, and if it is the compressive state of stress is there, then you can say that it decreases the natural frequencies. So what happens is, in order to access this type of pre-stressed modal analysis, first you need to perform a simple static analysis, and from that simple static analysis you need to say bring this solution as an input to this modal analysis. Don't worry, we are going to see this example as well in the coming lectures. Then so coming to the equations, so what happens, the basic equation as I've told you before, Ku equal to F, or say Kx equal to F, where this is the stiffness, this is the force matrix, this is the say displacement matrix. What happens is, from this performing static structural analysis, we are going to get a stress stiffness matrix. So once we obtain the stress stiffness matrix, we are going to add this stress stiffness matrix, which is denoted by S, to this already existing stiffness matrix of K. So the equation becomes K plus S minus omega I square m into psi I equal to 0. So what happens, the free vibration equation has been modified to include the S term, which is nothing but the stress stiffness analysis, which comes from structural analysis. So with this we have completed this theory regarding the free vibration analysis as well as the pre-stressed vibration analysis. So in the next lecture we are going to see how we can perform different types of modal analysis, and what are the results we are going to get, and how to interpret those results in the coming lectures. Thank you.